So this is going to be a video on fluid balance for fellow nursing students who might find that this chapter is a lot to digest, and it is. I'm going to try to do this in a two-part video. The first part I'm going to go over actual fluid balance, and the second part I'll go over the normal clinical manifestations of the various types of electrolyte imbalances that we can see. All right, so first off, you'll hear the terms hypervolemia and hypovolemia. It sounds similar to volume, and that's because it is. It's the Latin or Greek word or some other language. It means volume, though. So hyper is high, hypo is low. I hope you know that already. Um, there are multiple fluid compartments. There's the intracellular fluid, abbreviated as ICF. That accounts for about 40% of your total body weight and about 2/3 of your total fluid. And extracellular fluid, which includes your plasma. However, it's not just your plasma, meaning it's not just your blood. It's also the fluid in between your cells, the interstitial fluid. This is about 1/3 of your total fluid normally. An interesting thing to remember is because the metric system is awesome, 1 liter of water is the same, it weighs 1 kilogram. So if they've lost a kilogram of body weight in a day, they lost a liter of water that day. There's no way they burned a kilogram of fat that day unless they were doing some crazy, crazy stuff. We're not going to worry about that. So generally speaking, the way we monitor fluid status is their daily weight, intake, and output. Intake is how much fluid they take in. This includes water, it includes food, it includes medicine that comes in a fluid form, uh, and how much fluid that comes out, which includes urine, it includes blood, it includes anything like that, okay? And feces as well, especially if they have diarrhea. Yeah, so luckily the metric system makes it really easy. 1 kilogram is 1 liter. Very easy to remember. All right. So electrolyte balances in fluid compartments are different. The plasma is going to have its primary electrolyte be sodium. It'll have small amounts of potassium and magnesium and calcium as well. As far as anions go, it's mostly chloride. Makes sense, right? Sodium chloride, and it'll have moderate amounts of bicarbonate and protein. So it's still a bit of that, but not nearly as much as it has chloride. It'll also have small amounts of phosphate and some very negligible amounts of other negatively charged ions as well. Intracellular fluid is going to have huge amounts of potassium. This is very important. We're going to talk about hyperkalemia later, and I want you to remember that there's a lot of potassium inside the cells. And so you can imagine if cells start dying, like necrosis, rhabdomyolysis, or other problems like that occur, then they release all of the potassium that was once inside of them into the extracellular fluid, and that can cause problems in and of itself. So it also has small amounts of sodium and magnesium. The anions in the intracellular space mostly is going to be phosphorus. It's also going to have high amounts of negatively charged proteins, and it'll have some small amounts of bicarbonate and chloride as well. Okay, normal electrolyte lab values. I highly recommend, if you're watching this video, you pause it here and write these down. Make yourself some flashcards of these. They are incredibly important to know. It's important to note that each individual place where you may work might have their own idea of what normal lab values look like, but these ranges that I have here will be close to anything you'll find anywhere. They're all going to be around the same ballpark. Sodium generally is 135 to 145 milliequivalents per liter. Potassium is 3.5 to 5.0. I have heard some ranges say as high as 5.3, but I think it's better to be conservative with potassium. Magnesium is 1.5 to 2.5 milliequivalents per liter. Calcium is not in milliequivalents per liter. Keep that in your head. You don't want to write down their calcium level was 8.9 milliequivalents per liter. That's different than milligrams per deciliter. Okay? So, calcium, both total calcium and ionized calcium, are measured in milligrams per deciliter. And total calcium should be 8.6 to 10.2. And ionized calcium will be 4.6 to 5.3 milligrams per deciliter. Ionized is like just by itself. Sometimes calcium can be it's very protein bound, And so when we're measuring total calcium levels, we're measuring the amount that's on proteins, not just the amount that's free by itself. Um, that's why we measure these differently. You can imagine, because it's protein pound, that it is going to have some effect on certain medications that utilize proteins for their mechanism of action. Anions, bicarbonate, normal is 22 to 26. Chloride is 96 to 103, or 106, I'm sorry. And phosphate is 2.4 to 4.4. Now, a little note just for your benefit: the majority of phosphorus in the body is found as phosphate. That's PO4, 3 negative. And so you'll hear phosphorus and phosphate kind of, they'll talk about them interchangeably. It's just that PO4 is how we normally find phosphorus in the body. It's bound to 4 oxygens, giving it a triple negative charge. Okay. So fluid dynamics. There are 4 ways that fluid tends to move. There's diffusion, which is very simple, just molecules themselves move from an area where there's a high concentration of them to an area from a low concentration, right? Things like to move downhill, high to low, right? That's not the water moving, though. That is the stuff in the water, the sodium, potassium, all of those things moving. So if you have inside a cell where, let's say hypothetically, we're talking about sodium, where it's relatively low, and outside of the cell where there's high amounts of sodium, and inside the cell there's high amounts of potassium, and outside the cell there's low amounts of potassium. That's just how the sodium potassium pump works. It moves these across the cell normally, but the sodium potassium pump has to overcome this force because they want to be equal. The cell's potassium wants to get out of the cell, and the extracellular sodium wants to get into the cell until both of them are at the same level. That's not good. We don't want that. So the sodium potassium pump will take two. It'll take 2 potassium from in the cell, or I'm sorry, it'll bring 2 potassium into the cell and kick 1 sodium out of the cell. And it'll keep doing that to try to keep them at the same normal level. Facilitated diffusion is where a protein carrier molecule is used to facilitate diffusion of a larger molecule into the cell, right? So, for example, you have glucose, which is a really large molecule, and it can't just go through that cell membrane like some things can. It's too chubby. It's like it can't fit through the door. And so it needs somebody to open up a bigger door and let it in. And this is what insulin does. That's facilitated diffusion. It's not the only case of it in our body. There's lots of cases, but just know that it exists. Active transport uses energy. So I mentioned earlier that sodium potassium pump, right? It doesn't move them against their concentration gradient for free. Like, it takes a lot more energy to roll a tire up a hill than it does to let the tire roll itself down the hill, right? And this is what active transport does. These are our pumps and stuff in cells, which use ATP to move more potassium into the cell, despite the fact that the cell's already high in potassium and the outside is low in potassium. That takes energy. And to move sodium from inside the cell outside the cell, despite the fact that outside the cell there's a lot of sodium and inside the cell there's a little, you're moving it uphill. So that takes energy. So that's active transport. All these other ones don't take energy. Active transport's the only one that uses ATP. Okay? Osmosis, I wrote a little bit here because I've talked to some people and they tend to get confused, because remember that rolling up a hill, rolling down a hill, they think, okay, so if it's easier to move something from an area of high concentration to an area of low, why is it that water moves from an area where there's a high concentration of why water moves from an area of low concentration of ions to an area of high concentration of ions and it doesn't take energy? Well, that's because the water is low concentration if you're in an area of high concentration of ions. So if you have 50% water and 50% ions, they're the same. If you have 60% ions, you now only have 40% water. And so there's less water now. So if you have an area where there's a higher concentration of water, that that means automatically there's a lower concentration of ions. Osmosis is just diffusion, but with water instead of ions. That's all it is. I know I probably said that in a convoluted way, but I hope it's simple in principle. The idea is water will do what ions do, but water cares about the balance of water, not the balance of ions. So water will move from an area of a low concentration of ions, because that's a high concentration of water, to an area of a high concentration of ions, because it's a low concentration of water. It's still moving downhill. It's just we're talking about the concentration of water here, not the concentration of ions. I hope that makes sense. We're moving on. All right, so osmotic movement can be described based on the osmotic gradient. So remember what I just said, right? We just talked about how water cares about water, not about ions, right? And so that's important, because this is what we're referring to when we're talking about hypo or hypertonic solutions, or an isotonic. Isotonic is what I described when I said the water inside the cell and the water outside the cell are the same. And it doesn't have to be 50% water, 50% electrolytes. The inside of the cell can be 60% electrolytes, and the outside could be 60% electrolytes. As long as the concentration of water is the same inside the cell and outside the cell, and we don't have a gradient, then that's an isotonic solution. Now, a hypotonic solution means that there is less ions inside the cell than there are outside the cell. Now, that means there's more water inside the cell than there is outside the cell. So that means that the water wants to move inside the cell. Does that make sense? Because water flows downhill, right? And so the cell is going to grow because it's filling with water. It's going to grow and grow until it bursts. In the case of blood cells, we call that hemolysis or hemolysis. Hemo meaning blood, lysis meaning destruction. So death of the blood cells. That's what a hypotonic solution does. A hypertonic solution has a higher concentration of ions in the solution than it has in the cell. So that means that there is less water in the solution than there is water in the cell. That means the water wants to flow downhill out of the cell into the solution. We end up with dehydrated cells. They kind of shrink and shrivel up. Now, a way that was explained to me that helps me keep these straight is the O in hypotonic looks round, and it makes me think of a swollen cell. And the E in hypertonic looks shriveled because it's got those ridges, right? And so that makes me think of a shriveled up cell. I hope that helps you too, even if for no other reason than it's kind of a silly way to remember it. All right. So fluid pressure. So we talk about two main pressures when we talk about fluid dynamics. Hydrostatic pressure and colloid osmotic pressure, otherwise called oncotic pressure. The major colloids which affect the oncotic pressure of the blood are going to be proteins like albumin, especially albumin. I think that's like 60% of the protein in the blood is albumin. So plasma has large amounts of proteins, whereas the intracellular fluid doesn't have nearly as many. This causes the blood to gradually pull fluid out from the cells. Now, the blood is under pressure as well. This is hydrostatic pressure. Hydrostatic pressure is just the force of fluid on the wall of the container holding it. Now, if that container is steel, who cares? Not a big deal. But if that container is a cell membrane or a blood vessel, that force of that fluid causes the fluid to kind of leak out of that container into the surrounding areas. This is a good thing. We want this, but in excess, this can become a bad thing. Let's talk about that. We're going to go over fluid movement in the capillaries. So there are two ends of a capillary, the venous end and the arterial end. At the arterial end, because arteries are under pressure, we have a high hydrostatic pressure. And at the venous end, we have a low hydrostatic pressure because veins are not under a lot of pressure. I think they're like 2 or 3 millimeters of mercury. That's it. Now, both ends have the same colloid osmotic pressure. That's because the blood in your veins and the blood in your arteries is the same blood. It's just carrying less oxygen and more carbon dioxide depending on which side you're on, right? So the high hydrostatic pressure on the arterial end is going to push the fluid and make it leak into the tissue, leaving the vascular space. Now on the venous end, because it's got a low hydrostatic pressure, they're going to pull the fluid back in because now that blood colloid osmotic pressure has an opportunity to be stronger than the hydrostatic pressure and start to enact its force. So hydrostatic pressure pushes, colloid osmotic pressure pulls. And that's kind of how the capillaries work. So on the arterial end, the push is stronger, so fluid leaves. On the venous end, the pull is stronger, so fluid comes in. And ideally, those kind of happen where the point where they're the same is kind of in the middle. So you have as much time where it's pushing out as you do where it's pulling in, and your fluid balance remains about normal. Now, there are situations where your hydrostatic pressure might be too strong, such as the case when you have high blood pressure. And this allows it to be stronger than the colloid osmotic pressure for a longer period of time. And this can cause edema, buildup of fluid in the tissues. Another thing that could happen is maybe you have liver disease, or you don't have enough nutrition, you're malnourished, or maybe you have kidney disease, and for whatever reason, you don't have enough protein in your blood, right? It's being lost in your urine, your liver's not making it, or you just aren't getting it in your diet. In which case, the same effect is seen. The hydrostatic pressure is stronger than the colloid osmotic pressure for a longer period of time. Not because the hydrostatic increased here, but because the colloid osmotic decreased. This means there's more time for blood to be pushed out than there is for blood to be pulled in, and you end up with edema there as well. And then there's also the other things where maybe you have too much protein in your blood, or maybe you don't have enough blood pressure, and then you end up with dehydration of the tissues. Your skin becomes dry, everything else becomes dry, because now you have stronger colloid osmotic pressure, and so it's pulling more fluid into your vascular space and out of your tissues. All of these are bad. We want it balanced, right? We want them to be at the same level. I hope that makes sense, because we're going to move on. Okay, so we can actually change the fluid balance intentionally. There are things we can do through the use of mechanical devices like compression stockings, or through the use of medications to make it so that fluid goes into the compartment we want it in, right? So let's say we want to shift the fluid from the hydrostatic, or I'm sorry, we want to shift the fluid from the tissue to the blood, right? They have edema, right? And we want to lower that edema. I'm sure you've heard by now that we would put compression stockings on them, but have you ever thought of why? It increases the hydrostatic pressure of the tissue. See, we don't just have to talk about the blood. Both the blood and the tissue have these effects. And if you increase the hydrostatic pressure of the tissue, then this is going to cause the tissue to push fluid into the blood. Does that make sense? I really hope it does. If it doesn't, leave a comment and I'll answer any questions you may have. Now, you can also give medications, like you can give albumin via IV, which will increase the osmotic pressure of the blood to pull fluid into the blood. There's osmotic diuretics, which increase the osmotic pressure and help excrete more fluid through the kidneys by the use of osmotics, or proteins and things that increase the osmotic pressure, pulling the fluid. So there's lots of things we can do. I just want your mind thinking about those kinds of things while we go through this lesson. All right. So we're also going to talk about the RAAS, or RAS. Some people call it the RAS system. I think that's a bit redundant because it stands for renin, angiotensin, aldosterone system. So calling it the RAS system to me is like calling it the renin, angiotensin, aldosterone system, which to each their own. Anyways, the RAS system is triggered by a decrease in renal perfusion. This can happen from a low amount of blood volume. It can happen from stenosis of the renal artery, so like narrowing of the renal arteries. But whatever causes it, it triggers the release of renin. Renin is a chemical that triggers angiotensinogen to convert into angiotensin 1, which is still not active, by the way. Angiotensin 1 needs to interact with angiotensin converting enzyme, or ACE, to convert to angiotensin 2, its active form. That's why we use things like ACE inhibitors, which block that enzyme, to lower people's blood pressure, because this raises the blood pressure. Angiotensin 2 serves several important functions. I'm not going to go into all of its individual functions because it's quite a list. Instead, I'm just going to say that it activates the sympathetic nervous system, which of course is fight or flight. That's going to raise the blood pressure. It activates the release of aldosterone, which stimulates the retention of salt and by the kidneys, which indirectly stimulates the retention of water, and it also stimulates the thirst center. So basically, when you think of angiotensin 2, think that it increases your fluid balance or fluid in your vascular space, and it increases your blood pressure. If you think of it like that, it'll make perfect sense. It also increases your sodium, so keep that in mind as well. All right. All right, so this would be the first slide of the next video. I'm going to end this video here, and we'll continue with the next one, starting with hypernatremia, as you see. I hope you learned something in this video. If you have any questions, please feel free to leave a comment, and I'll get back to you on those. And happy nursing.